Okay. Um, so probably you've seen before that root 2 is not a rational number. Okay. And there's a bunch of. Let's see. Like what that means is that if we have this picture of this line, slice it right down the, we'll kind of like divide the rational numbers cleanly, I guess not really in half, but cleanly into two parts. Whereas if you cut 0, it's not as clean, like number 0 when you cut it. Okay. So basically, well, I like to think of it like, if you cut at root 2 perfectly, where like none of the cake gets on the knife, anyways, you kind of make a mess or something. Okay. To have, well, we have this word for it called, okay. First of all, what do we mean? Okay. I cut. What is that? It's just an ordered pair. Such that B is the rational numbers. Okay. A intersect B is the empty set. A and B are non-empty, both of them. And we want to keep in mind like this idea that we're cutting. So if we're cutting it into two like A and B, so we want everything in. And so we'll say for all A and A, B and B, A is less than B. Okay, that's what a cut is. Okay, and let's think about this example of root 2. When we, because root 2 is not a, what does it mean to have a clean cut? Well, it means element, and B has no least element. So that's another definition. Okay, cut in the rational numbers. Okay, the gap if A has no greatest element and B has no least element. Okay, let's just do a quick example. We want to show how root 2, okay. So let A, so basically this is going to be the set of all rational numbers. Basically, they should satisfy either x is less than or equal to 0. I'll say x is less than 0, or the rational numbers which are greater than or equal to 0 and less than 2. Okay. And then B, that's going to be all the rational numbers that are positive okay, and we want to show is a gap. Well, part of that is showing it's a cut with a special. We need to show that any element. Okay. Then either A is less than 0 or A is greater than or equal to 0 and A squared is less than 2. Okay. Then since B is in B is greater than 0. So A is less than 0, which is less than B, so A is less than B. Okay. The other case is that A B squared is bigger than 2, and now we want to show that A is less than B. Okay. So if an A squared is less than 2 and B squared is greater than 2, suppose for a contradiction that A is not less than. And now here's where we need the fact that less than on the rational numbers is a linear order. Okay. But either A is less or A is greater than B. If A is less than B, we're done. So we're not in that case, contradiction. So if A equals B, then A squared equals B squared. But A squared is less than, to have a number being less than itself. So this is a contradiction. Okay. Similarly, if A is greater than B, then since A or greater than or equal to 0, A squared is going to be bigger than BA, which is going to be bigger than, which is going to be bigger than B squared. And then that's bigger than sensitivity. You see that 2 is bigger than 2. And that's a contradiction. Okay. Element of B. Okay. In particular, A intersect B is empty because if there's something in both, it would be less than itself, which is impossible. Okay. Let R be any rational number. If R is negative, if R is greater than or equal to 0, then either R squared equals 2, R squared is bigger than 2, or R squared is less than 2. If R squared is bigger than 2, then R is in B, and then R squared equals 2. This is impossible from first year. You write R in lowest terms. You write R squared equals 2 and like cross multiply. Okay, so what that means is that every rational number is either in B or A. So that, okay, so let's see, what do we have? Every element of A is less than every element of B. The union of A and B is the rest. So, and we want to show we have a gap, is a cut of Q. We want to show we have a gap in Q. Okay, so we want to show that right, A has no greatest element. Well, suppose P is greater than or equal to 0 and 2. Now we just have to solve like a little problem. We want to make sure that P over Q is not the greatest element. P over Q plus 1 over n, so we'll square it. So we're going to choose n to be really large. When you square this, you get plus 2p over qn plus 1 over n squared. And so what we want is for this number, we want this to be less than 2 minus p squared over q squared. Okay. That's what we want. Or another. Okay, so let like r just be 2 minus p squared over q squared. And so 2p over q is at most like, say, 4. So we're going to solve 2p over qn plus 1 over n squared less than r. Okay. But 2p, that is definitely less than, so p over q is almost 2. So this is less than 1 over 4 over n, and 1 over n squared 5 over n. So let's just make 5 over n to be less than r. So take n to be greater than 5 divided by r. Okay, and so if n is greater than 5 over r, then what happened? Well, then p squared over q squared plus 2p over qn plus 1 over n squared. That's less than 2 plus, well, if n, that's like 2p over q times r over, this is less than 1 over n, which is less than r over 5. And then p over is less than 2. So this is 2 plus 4r over 5 plus r over 5. And r is just 2 minus p squared over q squared. Oh, wait, I should have left the p squared over q squared till the end. So r is less than, so r is 2 minus p squared over q squared plus p squared over q squared, we get 2. Okay, so that means that p over q plus 1 over n is still 1 over n is bigger than p over q. So p over q is not the greatest element of A. And p over q is just an arbitrary element of A. So A has no greatest element. We can do the same kind of thing, except, we do the same kind of thing, and we do something similar. Non-trivial property of the integers. We needed the following fact. We needed the fact that if we have any rational number q, then there exists an integer and that's allowed us to choose an integer n, which is bigger than 5 over r. R is really small, so maybe like 5 over r is like some q. Okay. So this tells us that A has no least element. Sorry, it tells us A has no greatest element and B has no least element. There's one last thing is to show that A is pretty clear. 0 is in A and like 2 is in B, since 2 squared is bigger than 2. So this really tells us that A and B, AB is a gap. Okay. So now, according to our definition of gap, the square root of 2 gives a gap. And that was our kind of like one of our motivation was that there is this hole in this number line. Okay. So that is why we call things gaps. Okay. And then, you know, as an exercise, let's say R to be like an minus 1, B1, B2. Let's that be a non-repeating. This is the rational number, be a non-repeating decimal representation. Okay. R can be used to construct it in the rationals. Okay. Okay, and then one more thing is that, okay, here whenever you have a non-repeating decimal, so you know, in other words, or sorry, of course that's not a rational number. Whenever you have a non-repeating decimal, irrational number, and so that can be also used to split the rational numbers into two pieces, and you also get a gap. Okay, it doesn't split cleanly, so we have like something called a rational cut. So let's define that. Okay, let Q be a rational number. Let's define CQ just to be AQ, BQ. This is going to be, we're going to cut the rational numbers less than Q and the rational numbers greater than or equal to 2, Q. So AQ is going to be all the R's in Q that are strictly less than Q, and BQ is going to be all the rational numbers that are bigger than or equal to Q. Okay. Then CQ is a cut of the rationals, and we call this a rational cut. Okay. And when we cut the rationals at a rational number, we have the choice, the rational number into A or B, and we're going to always choose to put it in B. Okay. It's just an arbitrary choice. Okay, so let us now just take a break for about 10 minutes, or no, let's minutes. And we just want to continue building up the cuts. And our kind of goal, I'll just tell you, our goal is the least upper bound property, which says we want to construct, like it says, if is a subset of the real numbers, U is non-empty, U is bounded, then U has a least upper bound. Okay, and we know the rationals don't have the least upper bound property because that is what a gap represents, a set without a least upper bound. Okay. Okay, so let us take a 7-minute break now.